And now in this lecture we'll answer two questions. In the first question, we can find out the size of this angle ABC equals to x, so we have to find out the value of angle x. The second question, we'll find out the length of this line segment AD equals to x. So we have to find out the length of x. So let's start with the first question. In the drawing, we have quadrilateral ABCD. Those two angles are both equal to 80 degrees in their sizes. In addition, we know that AD equals to AB equals to BC. Again, our task is to find out the size of this angle ABC is equals to x. We have to find out the value of angle x. So first of all, we will join point B and D together by a straight line. Again, we will join points B and D together by a straight line. By joining points B and D, we divided this quadrilateral ABCD into two triangles. The first triangle is triangle BCD, and the second triangle is this triangle ABD. So we know that AB equals to AD. Again, AD equals to AD according to what is given as a question. We have a rule that says that in front of equal sides in the triangle there are equal angles. Again, in front of equal sides in the triangle there are equal angles. So in front of those two equal sides in triangle BAD, we have those two angles that must be also equal to each other and their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. In the triangle ABD, the sum of the angles must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So alpha plus alpha is 2 alpha plus 80 degrees. In total, the sum of those angles must be equal to 180 degrees according to the rule that I mentioned. So I write it down. In triangle ABD, the sum of the angles must be equal to 180 degrees. That is to say 2 alpha plus 80 degrees. In total, the sum of those three angles must be equal to 180 degrees. And again, in triangle ABD, the sum of its three angles must be equal to 180 degrees. 2 alpha plus 80 degrees equals to 180 degrees. Here we subtract 80 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 80 degrees is 100 degrees. So 2 alpha equals to 100 degrees. Here we divide this equation by 2. And finally get the missing angle alpha equals to 100 degrees over 2 is 50 degrees. So those two angles are both equal to alpha, and therefore each of them is equal to 50 degrees in its size. So write it down. What is the size of this missing angle BDC. From the drawing, it's very easy to see that the size of this missing angle BDC is equal to 80 degrees or 50 degrees. Again, 80 degrees or 50 degrees equals to the size of this angle BDC. So 80 degrees or 50 degrees is 30 degrees. So the size of the missing angle BDC is equal to 50 degrees. Again, the size of this missing angle BDC equals to 30 degrees. $80 minus 50 degrees is 30 degrees. The next step, we define angle BCD. This angle is beta. And we will implement the law of sines in this triangle ABD. So, I repeat quickly on the law of sines. The law of sines is true in any triangle. This is triangle ABC that could be any triangle. The size of this angle BAC is equal to capital A degrees. The size of this angle ABC equals to capital B degrees, and the size of this angle ACB equals to capital C degrees in its side. In addition, we know that the length of side AB of triangle ABC is equals to 3 units. Side AC of this triangle ABC equals to B units in its length. This is side BC, this is equals to A units in its length. So this triangle ABC that could be any triangle, according to the law of sines, the following equation is true. A or sinus A equals to B or sinus B equals to C or sinus C. Again, A over sinus A equals to B or sinus B equals to C over sinus C. So we can implement the law of sines in our triangle ABD of the fact that the law of sines is true in any triangle. In this triangle ABD, according to the law of sines, BD over sinus 80 degrees equals to BA over sinus 50 degrees. Okay, again, according to the law of sines, this triangle ABD BD over sinus 80 degrees equals to BA over sinus 50 degrees. We will substitute 80 degrees by 2 times 40 degrees in this equation, and we will substitute 50 degrees by 90 degrees minus 40 degrees. So we have BD. BD is the missing side, so we leave it as it is. Or sinus 80 degrees. Sinus 80 degrees is sinus 2 times 40 degrees. Equals to BA. So we define the length of side BA as A, and because of the fact that according to what is given as the equation, BA equals to AD equals to BC, BC and AD must be also equal to A units in the other, because of the fact that those three sides are equal to each other. So BC equals to A units in its length, and AD also equals to A units in its length, according to what is given as the question. AD equals to AB equals to BC equals to A. So BD or 180 degrees equals to BA. BA is A according to our definition, or sounds 50 degrees. 50 degrees is 90 degrees minus 40 degrees, so it is sinus 90 degrees minus 40 degrees. Here we will implement two trigonometric identities in our equation. Repeat again. We will implement the following two trigonometric identities in our equation. The first trigonometric identity is as follows. Sinus 2 alpha equals to 2 times sinus alpha cosine alpha. This is the first trigonometric identity. And the second trigonometric identity is as follows. Sinus 90 degrees minus alpha equals to cosine alpha. So according to this trigonometric identity, sinus alpha equals to 2 times sinus alpha cosine alpha. We will get that sinus 2 times 40 degrees equals to 2 times sinus 40 degrees times cosine 40 degrees. So in this side of the equation we have BD over 2 times sinus 40 degrees times cosine 40 degrees. On the other side of this equation we have A over sinus 90 degrees minus 40 degrees. According to this trigonometric identity, sinus 90 degrees minus alpha equals to cosine alpha, we will get that sinus 90 degrees minus 40 degrees equals to cosine 40 degrees. So in total, we should find out that BD over 2 times sinus 40 degrees times cosine 40 degrees equals to A over cosine 40 degrees. We have here cosine 40 degrees on both sides of this equation, so cosine 40 degrees will get cancelled. After I cancel cosine 40 degrees, in this side of the equation we left only with BD over 2 times sinus 40 degrees. And on the other side of this equation, we left only with A. So in total, we actually found out that BD over 2 times sinus 40 degrees equals to A. Here we will multiply this equation by 2 times sinus 40 degrees. And we get that in this side of the equation we have to with BD equals to 2A times sinus 40 degrees. So if we found out that the missing side BD is equal to 2A times sinus 40 degrees in its length. This is side BD that is equals to 2A times sinus 40 degrees in its length. So write it down. In the next step, implement the law of sines in this green triangle BCD. Repeat again. We will implement the law of sines in this green triangle BCD. According to the law of sines, in this green triangle BCD, the following equation is true. BD over sinus beta equals to BC over sinus 30 degrees. Repeat again. In this green triangle BCD, according to the law of sines, the following equation is true. BD over sinus beta equals to BC over sinus 30 degrees. We already found out that BD equals to 2A sinus 40 degrees. So let's solve BD by 2A times sinus 40 degrees. So BD equals to 2A sinus 40 degrees. The denominator we have sinus beta, so it is over sinus beta. That equals to BC over sinus 30 degrees. BC equals to A units in itself according to our definition, so we substitute BC by A over sinus 30 degrees. Sinus 30 degrees is 1/2. So we substitute sinus 30 degrees by 1/2. So in this side of the equation we have A over 1/2. A over 1/2 is 2A. So in total we actually found out that A sinus 40 degrees over sinus beta equals to 2A. We have 2A on both sides of this equation, so 2A will get cancelled. After I cancel 2A, this side of the equation we left only with sinus 40 degrees over sinus beta. On the other side of this equation, we left only with 2A over 2A is 1. We left only with 1. Here we will multiply this equation by sinus beta. And finally we get that sinus 40 degrees equals to sinus beta. Repeat again. We actually found out that sinus 40 degrees equals to sinus beta, or sinus beta equals to sinus 40 degrees. If sinus beta equals to sinus 40 degrees, it means that beta equals to 40 degrees. The size of again beta is 40 degrees. This is the first solution for beta. We have another solution for angle beta. We use a third trigonometric identity that says that sinus alpha equals to sinus 180 degrees minus alpha. According to this trigonometric identity, we get that sinus 40 degrees equals to sinus 180 degrees minus 40 degrees. Repeat again. According to this trigonometric identity, sinus 40 degrees equals to sinus 180 degrees minus 40 degrees. 180 degrees minus 40 degrees is 140 degrees. So it is sinus 140 degrees. Those two sides of the equation are equal to each other. That is to say, sinus 40 degrees equals to sinus 140 degrees. And we already found out that sinus 40 degrees equals to sinus beta. And again, we already found out that sinus 40 degrees equals to sinus beta. Write it down here. Sinus 40 degrees equals to sinus beta. But we just right now found out that sinus 40 degrees equals to sinus 140 degrees. So we can write here that sinus 40 degrees equals to sinus 140 degrees. And from this equation, sinus 140 degrees equals to sinus 40 degrees equals to sinus beta. Those two sides of the equation are equal to each other. We will get that sinus 140 degrees equals to sinus beta. If sinus 140 degrees equals to sinus beta, it means that beta equals to 140 degrees in its size. This is according to the second solution for beta. While according to the first solution for beta, beta equals to 40 degrees in its size. So we have two solutions for beta. Beta could be equal to either 40 degrees or to 140 degrees. In its size. So, actually, in the green triangle BCD, this is angle beta. From the drawing, it is very easy to see that angle beta is definitely greater than 90 degrees. Again, this is angle beta. Angle BCD equals to beta. And angle BCD is equals to beta. It's definitely greater than 90 degrees. Therefore, angle beta could never be equal to 40 degrees. That is less than 90 degrees. So we cancel this solution for beta, and we take into account only the second solution for beta. That is beta equals to 140 degrees in its size. So, now we found out that this is angle beta that equals to 140 degrees in its size. In this green triangle BCD, the sum of the angles must be equal to 180 degrees. So which angles we have in this green right triangle BCD? This angle equals to 30 degrees plus this angle, this equals to 140 degrees. Plus this third missing angle, this is actual angle DBC. In total, the sum of those angles must be equal to 180 degrees, according to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. So repeat again, in the green triangle BCD, the sum of the angles must be equal to 180 degrees. That is to say, 30 degrees plus 140 degrees plus the third missing angle DBC. In total, the sum of those angles must be equal to 180 degrees. +30 degrees plus 140 degrees is 170 degrees. plus the third missing angle is actually angle DBC. In total, the sum of those figures must be equal to 180 degrees. Here we subtract 170 degrees from this equation, and finally get that the missing angle DBC is equal to 180 degrees minus 170 degrees is 10 degrees. So if you found out that this is the missing angle DBC, it is equal to 10 degrees in its size. Our task is to find out the size of this big angle, angle ABC. We have to find out the size of this angle, angle ABC. From the drawing, it is very easy to see that angle ABC in total equals to 50 degrees plus 10 degrees, that is 60 degrees. So if you found out that angle ABC is equal to angle X is equal to 60 degrees in its size. And that is the answer to the first question. Repeat again, if you found out that this is the missing angle ABC equals to X, and it is equal to 60 degrees in its size. So we finish with the first question. In the next step, I present you the second question of this lecture, and we will solve the second question by using two different methods. The second question, our task is to find out the length of this side AD is equal to X. And again, we have to find out the length of side AD is equal to X. So we have to find out the length of line segment X. So in the drawing, we have quadrilateral ABCD. It is given as the equation that AB equals to BP. In addition, we know that those two angles are both right angles. Again, our task is to find out the length of line segment AD is equal to X. We have to find out the length of line segment X. So first of all, we will join points B and D together by a straight line. By joining points B and D, we divided quadrilateral ABCD into two triangles. The first upper triangle is the right triangle BDA, and the second lower triangle is the right triangle BCD. So we implement the Pythagoras theorem on those two right triangles. The first step, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So first of all, we implement the Pythagoras theorem on this upper right triangle, triangle ABD. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in this upper right triangle, triangle ABD, BD squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. And again, in this upper right triangle ABD, according to the Pythagoras theorem, BD squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. BD is the missing hypotenuse, so we leave it as it is. This BD square equals to AB square. AB is also the missing side, so we leave it as it is. It is A equals to AB square plus AD square. AD is the line segment that we're looking for in this question. AD equals to X, therefore AD square equals to X square. So in total, according to equation 1, we should find out that dB square equals to AB square plus X square. This is according to equation 1. In the next step, we will implement the Pythagoras theorem on this lower right triangle DBC. Repeat again. Here by PT is a function for Pythagoras theorem. This right lower triangle DBC according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, equals to BC square plus DC square. Actually, it is given as a question that the length of this short line segment dP is 1. And the length of this line segment PC equals to 4. And therefore, in total, DC equals to 1 plus 4, that is 5. And again, DC equals to 5 and it's enough according to what is given as a question. So according to the Pythagoras theorem, in this right triangle DBC, the following equation is true. dB squared, that is the square of the hypotenuse, equals to BC squared plus DC squared. BD is the missing hypotenuse, so we leave it as it is. It is BD squared equals to BC squared. BC is also the missing side, so we leave it as it is. It is equals to BC squared plus DC squared. DC is 5, therefore DC squared is 5 squared, it is 25. So in total, according to equation 2, we should find out that dB squared, that is the square of the hypotenuse, equals to BC squared plus 25. This is according to equation 2, while according to equation 1, we already found out that BD squared equals to AB squared plus X squared. So we have two different equations for dB squared. Therefore, we get equation 3 that says that dB squared according to equation 1 must be equal to dB squared according to equation 2. dB squared according to equation 1 must be equal to dB squared according to equation 2. This is equation 3. So according to equation 3, dB squared according to equation 1 must be equal to dB squared according to equation 2. dB squared according to equation 1 equals to AB squared plus X squared. And it must be equal to dB squared according to equation 2. dB squared according to equation 2 equals to BC squared plus 25. So in total, according to equation 3, we should find out that AB squared plus X squared equals to BC squared plus 25. In the next step, we get equation 4. By implementing the Pythagoras theorem on this lower green triangle PBC. Again, we get equation 4 by implementing the potential theorem on this lower right green triangle PBC. According to the potential theorem in this lower right triangle PBC, PB squared, that is the square of the hypotenuse, equals to BC squared plus CP squared. Repeat again. According to the potential theorem on this green triangle PBC, PB squared, that is the square of the hypotenuse, must be equal to BC squared plus PC squared. And again, according to the potential theorem, on this green right triangle PBC, PB squared, that is the square of the hypotenuse, equals to BC squared plus PC squared. PB is the missing hypotenuse, so we leave it as it is. This is PB squared equals to BC squared. BC is also the missing side, so we leave it as it is. This is BC squared plus PC squared. PC is 4, therefore PC squared is 4 squared, that is 16. So in total, according to equation 4, we actually found out that PB squared equals to BC squared plus 16. But according to what is given as the question, AB equals to PB. Again, AB equals to BP according to what is given us in the question. And therefore, PB squared equals to AB squared. So we substitute PB squared in this equation 4 by AB squared. So I do not, because of the fact that PB equals to AB according to what is given as the question, we substitute PB in this equation 4 by AB. PB equals to AB, therefore PB squared equals to AB squared. And here we have it is equals to BC squared plus 16. So in total, according to equation 4, we actually found out that AB squared equals to BC squared plus 16. This is according to equation 4. Well, according to equation 3, we have already found out that AB squared plus X squared equals to BC squared plus 25. So copy again equation 3 here. According to equation 3, we have already found out that AB squared plus X squared equals to BC squared plus 25. And because of the fact that according to equation 4, AB squared equals to BC squared plus 16, we will substitute AB squared in this equation 3 by BC squared plus 16. And we get that according to equation 3, again AB squared equals to BC squared plus 16, according to equation 4. So AB squared is BC squared plus 16. And we have here plus X squared equals to BC squared plus 25. So in total, according to equation 3, we actually found out that BC squared plus 16, that is actually AB squared, plus X squared equals to BC squared plus 25. Here we have BC squared on both sides of this equation 3, so BC squared will get cancelled. After we cancel BC squared, on this side of the equation we left only 16 plus X squared equals to 25. So according to equation 3, I actually found out that 16 plus X squared equals to 25. Here we will subtract 16 from this equation, equation 3. If I get it according to equation 3, x squared equals to 25 minus 16 is 9. X squared equals to 9. Here we take root out of this equation. If I get that x equals to the square root of 9, that is 3. So she found out that this is line 7 AD is equals to x and x equals to 3. Line 7 AD is equals to x is equal to 3 units in its length. And that is the answer to the second question according to the first method. AD equals to x equals to 3 units in its length. In the next step, I present to you how to find out the length of this side AD is equals to x according to the second method. Again, our task is to find out the length of line 7 AD is equals to x. So in the second method, we will do a construction, that is to say, we will extend side DC of quadrilateral ABC by 4 units. Repeat again, we will extend this side DC of this quadrilateral ABCD by 4 units. It is given us the equation that dp equals to 1 and pc equals to 4. So we extend side DC of quadrilateral ABCD by 4 units. And we will define the edge of the extended line 7. This point is point Q. Repeat again that CB equals to 4 units according to our construction. This is line 7 CB and this equals to 4 units in itself according to our construction. We extended side DC by 4 units and therefore CQ equals to 4 units in its length. CD is one side of quadrilateral ABCD, therefore it is absolutely a straight line. CD is the straight line. When you extend the straight line by a straight line, the result CQ must be also a straight line. CQ is the straight line. If you focus on the upper side of this straight line CQ at point C, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the areas on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of this straight line? Straight line DQ. Which angles we have at the upper side of the straight line DQ at point C? We have this angle that is equal to 90 degrees plus this missing angle. Total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. According to rule 3. In the next step, I join points B and Q together by straight line. By joining points B and Q, get the right triangle BCQ. So in the next step, we will prove that those two right triangles can go into each other according to side angle side rule. Okay, again we will prove that this is the right triangle BPC, that it is can go into this right triangle BCQ according to side equal side rule. So we have to prove that this is the right triangle BPC. And we have to prove that this right triangle BPC can point to this right triangle BCQ according to side equal side rule. So why those two right triangles can go into each other? First of all, side PC of this right triangle PBC equals to side CQ of this right triangle BCQ. They are both equal to 4 units in their lengths and therefore they are equal to each other. So write it down. This is side PC of this right triangle PBC. And this equals to side CQ of this right triangle BCQ. And again, I should found out that side PC of the right triangle BPC equals to side Q equals to side CQ of the right triangle BCQ. They are both equal to 4 units and therefore they are equal to each other. Repeat again. Side CQ equals to 4 units in itself according to our construction. In addition, those two angles are both right angles and therefore they are equal to each other. So here, this is angle BCP. On that triangle BPC, this equals to this angle, this is angle BCQ. On the right triangle BQC. Okay, again, I should found out that angle BCP of the right triangle BPC equals to angle BCQ of the right triangle BCQ. They are both equal to 90 degrees and therefore they are equal to each other. And finally, this is side BC. This is the common side that belongs to both triangles. So I can find out that side BC equals to itself is a common side that belongs to both triangles. Repeat again. Side BC equals to itself is a common side that belongs to both triangles. So I can find out that those two right triangles can go into each other according to side equal side rule. So write it down. The right triangle BPC congruent. This is the sign of congruent to the right triangle BCQ according to side equal side rule. That is to say, I shall prove that those two sides and the angle that is included between those two sides in this right triangle BPC are corresponding equal to those two sides and the angle that is included between those two sides in this right triangle BCQ. And therefore those two right triangles can go into each other according to side angle side rule. Repeat again, those two sides and the angle that is included between those two sides in this right triangle BCP corresponding equal to those two sides and the angle that is included between those two sides in this right triangle BCQ. And therefore those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we will derive that BP equals to BQ. Okay, again, from the fact that those two right triangles can go into each other, we will derive that BP equals to BQ. BP equals to BQ according to the rule that says that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore there are two corresponding sides that is actually BP and BQ must be also equal to each other in their lengths. So if you found out that BP equals to BQ, and according to what is given as the equation, AB equals to BP. Therefore, all those three sides are equal to each other in their lengths. That is to say, AB equals to BP equals to BQ. AB equals to BP equals to BQ. But again, in conclusion, we found out that AB equals to BP equals to BQ. In the next step, we'll do a construction. That is to say, we will draw a circle around point B in such a way that point B will be the center of the circle and BA will be the radius of the circle. Repeat again, we draw a circle around point B in such a way that point B will be the center of the circle and BA will be the radius of the circle. So, we draw this circle, and the center of this circle is point B according to our construction, and BA is the radius of this circle also according to our construction. So, we define the radius of this circle BA as R. But because of the fact that we already found out that BA equals to BP equals to BQ, BP and BQ must be also the radius of the circle. So BP is the radius of this circle is equals to R. Likewise, BQ is also the radius of this circle is equals to R. Those three line segments AB, BP and BQ, all the radius of the circle is equals to R. And because of the fact that those three line segments are all the radius of the circle, it means that the circle must pass through points A, P and Q. Okay? But again, because of the fact that those three line segments AB, BP and BQ, are all the radius of the circle must pass through points A, P and Q. So this is actually the definition of a radius. It starts from the center of the circle, that is point B, and ends at point and the point on the circle itself. Therefore, point A must be located on the circle, point P must be also located on this circle, and point Q must be also located on this circle. You see from the drawing that those 3 points A, P, and Q are definitely located on this circle. According to what is given as a question, DA is perpendicular to AB. Again, DA is perpendicular to AB according to what is given as a question. This is the sum of perpendicular. DA is perpendicular to AB according to what is given as a question. But according to our definition, AB is the radius of this circle. So we can write down that AB equals to R, it is the radius of this circle. And because of the fact that DA is perpendicular to the radius AB, DA must be a tangent to this circle at point A. Therefore, DA is a tangent to the circle at point A. Likewise, from the same common sub point D, we have first of all tangent DA that is tangent to this circle at point A. Likewise, from the same common sub point D, we have secant DQ. Secant DQ cuts this circle at 2 points. Point P, actually secant DQ, this is secant DQ that cuts this circle at 2 points, P and Q. But again, secant DQ cuts this circle at 2 points, P and Q. And dP is the external part of secant DQ. Again, dP is the external part of secant DQ. And the length of this secant in total is equal to dQ units in its length. And repeat again that dP is the external part of secant dQ. So actually all the requirements of all of the secant tangent secant theorem are satisfied, and therefore we can implement in our drawing tangent secant theorem. And according to tangent secant theorem, the square of the tangent, that is actually dA square, equals to dP times dQ. Again, dA square equals to dP times dQ. So, the length of this tangent is dA, and the square of the length of this tangent is dA square. And it's equals to the product of the external part of dQ, that is dP, times the length of this secant in total, this is actually dQ. So it is dP times dQ. This is according to tangent secant theorem. So repeat quickly on tangent secant theorem. According to tangent secant theorem, if a tangent and the secant are drawn to a circle from the same external point, point P, this is the common external point, point P. From this common external point, point P, we have tangent PA that is tangent to this circle at point A. Likewise, we have also secant PC. Secant PC cuts the circle at those 2 points B and C. So according to tangent secant theorem, in our drawing, the following equation is true. The square of the tangent lengths equals to the product of the secant's whole length and its external part. Essentially, tangent square equals to the product of the external secant part times the whole secant. And again, PA squared, that is the length of the secant squared, and the length of the tangent squared, equals to PB times PC. Again, PA squared equals to PB times PC. The product of the external part of this secant is a B times by the length of the secant in total, this is PC. So PB times PC, that is the product of the external part PB by the length of the secant in total, that is PC. So PB times PC equals to PA squared. So PA squared equals to PB times PC. We already implemented the tangent secant theorem in our drawing. Here we have DA is tangent to this circle at point A. So the length of the tangent squared is dA squared equals to the product of the external part of secant dq, that is dp, times the length of the secant in total, that is dq. So dA squared equals to dp times dq. Again, dA squared equals to dp times dq according to tangent secant theorem. And again, according to the tangent secant theorem, if we focus on the common standpoint point D, from this common standpoint point D, we have tangent dA that is tangent to this circle at point A. Likewise, from the same common standpoint point D, we have secant dq that cuts the circle those 2 points P and Q. And therefore, according to tangent secant theorem, the following equation is true. dA squared, that is the length of the tangent squared, equals to dp times dq. According to what is given as a question, dA equals to x units in itself, that is line segment that we are looking for in this question. If dA equals to x, then dA squared must be equal to x squared. So we solve dA squared by x squared. And this equals to dp, according to what is given in the question, dp equals to 1 times dq. dq in total equals to 1 plus 4 plus 4, that is 9. Again, dq in total equals to 1 plus 4 plus 4, that is 9. So in total, we found out that x squared equals to 1 times 9, that is 9. X squared equals to 9. Here we take a root out of this equation and find again that x equals to the square root of 9, that is 3. So she found out that line segment AD is equals to x, line segment AD is equals to x is equals to 3 units in its length. So on both methods, we actually found out that the length of line segment AD equals to x is equals to 3 units. So we finish with the second method of the second question. In the next step, I'll summarize the lecture, that is to say, we repeat on the solution of the first question, and then we repeat on the solution of this second question on both methods. In the first question, our task was to find out the size of this angle ABC is equal to x. We have to find out the value of angle x. So in the drawing we have quadrilateral ABCD. We know that BC equals to BA equals to AD. In addition, we know that those two angles are both equal to 80 degrees in their sizes. And our task is to find out the size of this angle ABC is equal to x. We have to find out the value of angle x. So first of all, we join points B and D together by a straight line. By joining points B and D, we divided this quadrilateral ABCD into two parts, into two triangles. The first triangle is triangle BCD, and the second triangle, this triangle ABD. In the next step, we focus on this triangle ABD. We have the rule that says that in front of equal sides in the triangle, there are equal angles. So, in triangle ABD, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. And we also know that the sum of the angles in any triangle is equal to 180 degrees. That is to say, alpha plus alpha, that is 2 alpha, plus 80 degrees must be equal to 180 degrees in this triangle ABD. In the triangle ABD, the sum of its three angles must be equal to 180 degrees. That is to say, 2 alpha plus 80 degrees equals to 180 degrees. Here we subtracted 80 degrees from this equation and found out that 2 alpha equals to 180 degrees minus 80 degrees, it is 100 degrees. Here we divided this equation by 2 and found that the missing angle alpha equals to 100 degrees over 2, that is 50 degrees. So those two angles are both equal to alpha, and therefore each of them is equal to 50 degrees in its size. What is the size of this missing angle BDC? Angle BDC equals to 80 degrees minus 50 degrees. Again, the missing angle BDC, this angle equals to 80 degrees minus 50 degrees, that is 30 degrees. So angle BDC equals to 30 degrees in its size. We define this angle, the size of this angle BCD, this angle is beta, and then we implemented the law of sines in this triangle ABD. So I repeat quickly on the law of sines. Actually, the law of sines is true in any triangle. This is triangle ABC that could be any triangle. The size of this angle BAC equals to capital A degrees. The size of this angle ABC equals to capital B degrees, and the size of this angle ACB equals to capital C degrees. Likewise, the length of side AB is C units, the length of side AC of this triangle ABC equals to B units, and the length of side BC equals to A units. This triangle ABC that could be any triangle, according to the law of sines, the following equation is to A over sinus A equals to B over sinus B equals to C over sinus C. Actually implemented the law of sines in our triangle ABD. This is triangle ABD. According to the law of sines, this triangle ABD, the following equation is to this triangle ABD, BD over sinus 80 degrees equals to BA over sinus 50 degrees. Again, this triangle ABD, according to the law of sines, the following equation is to BD over sinus 80 degrees equals to BA over sinus 50 degrees. BD over sinus 80 degrees equals to BA over sinus 50 degrees. The next step, we substitute 80 degrees by 2 times 40 degrees, and we substitute 50 degrees by 90 degrees minus 40 degrees. And we should found out that BD over sinus 2 times 40 degrees equals to A over sinus 90 degrees minus 40 degrees. The next step, we implemented two trigonometric identities in our question. The first trigonometric identity is as follows. Sinus 2 alpha equals to 2 times sinus alpha cosine alpha, and the second trigonometric identity is sinus 90 degrees minus alpha equals to cosine alpha. According to the first trigonometric identity, sinus 2 alpha equals to 2 times sin alpha cosine alpha, we will get that sinus 2 times 40 degrees equals to 2 times sinus 40 degrees times cosine 40 degrees. We substitute sinus 2 times 40 degrees by 2 times sinus 40 degrees times cosine 40 degrees. So total this side of the equation we have BD over 2 times sinus 40 degrees times cosine 40 degrees. And the second trigonometric identity is sinus 90 degrees minus alpha equals to cosine alpha. According to this trigonometric identity, we get that sinus 90 degrees minus 40 degrees equals to cosine 40 degrees. So we substitute sinus 90 degrees minus 40 degrees by cosine 40 degrees. And we know that BA equals to A because of the fact that BA equals to BC equals to AD. We find one side of this freelance surface SA, so all the freelance surface must be also equal to A because they are equal to each other. So we substitute BA by A. Substitute BA by A. So if we found out that BD over sinus BD of 2 times sinus 40 degrees cosine 40 degrees equals to A over cosine 40 degrees. We have cosine 40 degrees on both sides of this equation, so this cosine 40 degrees will get cancelled. After cancelled cosine 40 degrees, in this side of the equation we left only with A, while on this side of the equation we left with BD over 2 times sinus 40 degrees. So in total, we shall found out that BD over 2 times sinus 40 degrees equals to A. Here, multiply this equation by 2 times sinus 40 degrees, and if we found out that in total that BD equals to 2A times sinus 40 degrees. This is the missing side. BD is equals to 2A times sinus 40 degrees in its length. In the next step, we implemented the law of sines in this green triangle BCD. According to the law of sines in this triangle BCD, BD over sinus beta equals to BC over sinus 40 degrees. But again, this green triangle BCD, according to the law of sines, BD over sinus beta equals to BC over sinus 40 degrees. And again, the green triangle BCD, according to the law of sines, the following equation is true. BD over sinus beta equals to BC over sinus 40 degrees. We only found out that BD equals to 2A times sinus 40 degrees, so we substitute BD by 2A times sinus 40 degrees over sinus beta equals to BC. BC equals to A according to our definition, so we substitute BC by A, and sinus 40 degrees equals to 1/2. So in total, in this side of the equation, we have A over 1/2 is 2A. So those two sides of the equation are equal to each other. That is to say, 2A times sinus 40 degrees over sinus beta equals to 2A. We have 2A on both sides of this equation, so 2A will get cancelled. After cancel 2A, in this side of the equation, we left only with 1. While on the other side of this equation, this side, we left with sinus 40 degrees over sinus beta. So in total, we found out that sinus 40 degrees over sinus beta equals to 1. Here we multiply this equation by sinus beta, and finally found out that sinus 40 degrees equals to sinus beta. If sinus 40 degrees equals to sinus beta, it means that beta equals to 40 degrees in its size. But we have another solution for beta. We use the first trigonometric identity that says that sinus alpha equals to sinus 180 degrees minus alpha. According to this first trigonometric identity, we will get that sinus 40 degrees equals to sinus 180 degrees minus 40 degrees. 180 degrees minus 40 degrees is 140 degrees. So to that, we should find out that sinus 40 degrees equals to sinus 140 degrees. And we already found out that sinus 40 degrees equals to sinus beta. Yes, sinus 40 degrees equals to sinus beta. Sinus 40 degrees equals to sinus beta, and we just found out that sinus 40 degrees equals to sinus 140 degrees. So we can add here that sinus 40 degrees equals to sinus 140 degrees, and for this equation, sinus 140 degrees equals to sinus 40 degrees equals to sinus beta. We will derive that sinus 140 degrees equals to sinus beta. Those two sides of the equation are equal to each other. Sinus 140 degrees equals to sinus beta. If sinus 140 degrees equals to sinus beta, it means that beta equals to 140 degrees in size. So according to the second solution for beta, beta equals to 140 degrees in size. And according to the first solution for beta, beta equals to 40 degrees in size. But because of the fact that if you look at the drawing, if we take a look on this drawing, in this again trial BCD, this is angle beta. From the drawing, it is very easy to see that angle beta is definitely greater than 90 degrees. If angle beta is greater than 90 degrees, angle beta will never be equal to 40 degrees, that is less than 90 degrees. So the first solution for beta could never be equal to 40 degrees. Now we took into account only the second solution for beta, that definitely beta equals to 140 degrees in size. This is angle beta is equal to 140 degrees in size. We know that the sum of the angles in any triangle is equal to 180 degrees, so the sum of the angles in this green rectangle BCD equals to 180 degrees. That is to say 30 degrees plus 140 degrees, plus this third missing angle, the angle DBC, in total the sum of those three angles must be equal to 180 degrees. Repeat again, in the green rectangle DBC, 30 degrees plus 140 degrees, plus the third missing angle DBC, in total must be equal to 180 degrees. 30 degrees plus 140 degrees is 170 degrees, so 170 degrees plus the size of the third missing angle, the angle DBC, in total must be equal to 180 degrees. Here we subtracted 170 degrees from this equation, we found out that the missing angle DBC equals to 180 degrees minus 170 degrees is 10 degrees. This is the missing angle DBC, that equals to 10 degrees in size. Our test was to find out the size of this angle ABC. Angle ABC in total equals to 50 degrees plus 10 degrees, that is 60 degrees. And again, the size of this angle ABC equals to 60 degrees. So angle X equals to 60 degrees in its size. So we finished to repeat on the first question, on the solution of the first question. In the next step, I repeat on the solution of the second question on both methods. In the second question, our test was to find out the length of this line segment AD or side AD is equals to x. We have to find out the length of line segment x is equals to AD. So in the drawing we have quadrilateral ABCD. We know that BP equals to 1, PC equals to 4. We also know that AB equals to BP. Those two sides are equal to each other. And we also know that those two angles are both right angles. Again, our test is to find out the length of side AD is equals to x. We have to find out the length of line segment x. So first of all, we join points B and D together by side line. By joining points B and D, we can deduce two right angles. We divided quadrilateral ABCD into two right angles. The first right angle is ABD, and the second right angle, the lower right angle, is DBC. So we implemented the Pythagoras theorem on both those two right angles. So first of all, we implemented the Pythagoras theorem on this upper right angle ABD. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this upper right angle ABD, BD squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. Again, this upper right angle ABD, according to the Pythagoras theorem, DB squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. BD is the missing hypotenuse, so this is this, and this equals to AB squared. AB is also the missing side, so this is this, plus AD squared. AD is x, therefore AD squared is x squared. So in total, we found out that according to equation 1, BD squared equals to AB squared plus x squared. In the next step, we implemented the Pythagoras theorem on this right lower triangle, triangle DBC. According to the Pythagoras theorem, in this right lower triangle, triangle DBC, DB squared, that is the square of the hypotenuse, equals to BC squared plus CD squared. But again, in the right lower triangle, triangle DBC, according to the Pythagoras theorem, the following equation is true. DB squared, that is the square of the hypotenuse, equals to BC squared plus DC squared. DB is the missing hypotenuse, so it is, so it is DB squared plus BC squared. BC is also the missing side, so it is, so it is equals to BC squared plus CD squared. CD in total equals to 1 plus 4, that is 5. Therefore, CD squared equals to 5 squared, that is 25. So in total, according to the equation 2, we should find out that BD squared or DB squared equals to BC squared plus 25. So we have two different equations for DB squared, equation 1 and equation 2. Therefore, we can do the equation 3 that says that DB squared according to equation 1 must be equal to DB squared according to equation 2. DB squared according to equation 1 equals to AB squared plus x squared, and it must be equal to DB squared according to equation 2. DB squared according to equation 2 equals to BC squared plus 25. So in total, if we found out that according to equation 3, AB squared plus x squared equals to BC squared plus 25. In the next step, we created equation 4 by implementing the Pythagoras theorem on the right green triangle PBC. This is the right green triangle PBC. According to the Pythagoras theorem, on this right triangle PBC, PB squared, that is the square of the hypotenuse, equals to BC squared plus DC squared. And then again, according to equation 4, I should find out that BB squared, that is the square of the hypotenuse, equals to BC squared plus PC squared. PB is the missing hypotenuse, so it is PB squared equals to BC squared. PC is also the missing side, so it is plus PC squared. PC is 4, therefore PC squared is 4 squared, it is 16. So in total, according to equation 4, we actually found out that BC squared equals to PB squared equals to BC squared plus 16. But according to what is given as the equation, PB equals to AB. PB equals to AB according to what is given as the equation, so we can substitute PB by AB. So substitute PB by AB. If PB equals to AB, then PB squared equals to AB squared, and equals to BC squared plus 16. So according to equation 4, we found out that AB squared equals to BC squared plus 16. This is according to equation 4, while according to equation 3, we only found out that AB squared plus x squared equals to BC squared plus 25. So we can substitute AB squared in this equation 3 by BC squared plus 16 from equation 4. We did it, and we found out that according to equation 3, AB squared is BC squared plus 16 plus x squared equals to BC squared plus 25. So then according to equation 3, we found out that BC squared plus 16, that is AB squared, plus x squared equals to BC squared plus 25. Here we have BC squared on both sides of this equation, so BC squared will get cancelled, and we cancel BC squared. On this side of the equation we left with 16 plus x squared, while on the other side of the equation we left only with 25. So in total we found out that 16 plus x squared equals to 25. Here we subtract the 16 from this equation, and we found out that x squared equals to 25 from 16, that is 9. X squared equals to 9, here we took out of this equation, and we found out that x equals to the square root of 9, that is 3. So we found out that the length of this line at AD is equals to x is equals to 3 units. So we finish with the repetition of the first method and the second question. In the next step, we repeat on the solution of the second method of this question. The second method of the second question. In the second method, we did a construction, that is to say, we extended side DC of quadrilateral ABCD by 4 units. Repeat again, we extended this side DC by 4 units. And we defined the extended side, the edge of the extended side, this point is point Q. Again, CQ equals to 4 units in itself according to our construction. DC is one side of quadrilateral ABCDs. So this is a side of a quadrilateral is absolutely a straight line. And when you extend straight line by straight line, the result DQ is also a straight line. So if you focus on the upper side of this straight line DQ at point Z, the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the areas on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line DQ at point C? We have this angle that is the right angle according to what is given as the equation, plus this missing angle. In total, the sum of those angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points B and Q together by straight line. By joining points B and Q, we create the right triangle, this right triangle BCQ. So in the next step, we proved that those two right triangles can go into each other according to sine and side rule. That is to say, we proved that this is right triangle PBC can go into this right triangle BCQ according to sine and side rule. So why those two right triangles can go into each other? First of all, those two sides PC and CQ, they are both equal to 4 and therefore they are equal to each other. In addition, those two angles are both right angles and therefore they are equal to each other. And finally, this is side BC, that is a common side that belongs to both triangles. So we can write down that BC equals to itself is a common side that belongs to both triangles. So in total, we found out that those two right triangles can go into each other according to side and side rule. But again, we found out in total that the right triangle PBC or BPC can go to the right triangle PCQ according to side angle side rule. That is to say, we can prove that what is side angle side rule. We found out actually that those two sides and the angle that is included between those two sides in this right triangle PBC are possibly equal to those two sides and the angle that is included between those two sides in this right triangle BCQ. Therefore, we actually prove that those two right triangles can go into each other according to side angle side rule. We have those two sides and the angle that is included between those two sides in this right triangle PBC are possibly equal to those two sides and the angle that is included between those two sides in this right triangle BCQ. Therefore, those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we will derive that those two hypotenuses are equal to each other in their lengths. That is to say, BP equals to BQ. BP equals to BQ. BP equals to BQ according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore they have two corresponding sides. That is to say, BP and BQ must be also equal to each other and their lengths. So BP equals to BQ, but we all, according to what is given as the question, AB equals to PB. Therefore, those three line segments, AB, BP, and BQ, they are all equal to each other and their lengths. So in total, we found that AB equals to BP equals to BQ. In the next step, we did the construction. This is to say, we drew a circle around point B in such a way that point B will be the center of the circle and BA will be the radius of the circle. Repeat again, we did the construction, that is to say, we drew a circle around point B in such a way that point B will be the center of the circle and BA will be the radius of the circle. So B equals to R, it is the radius of the circle according to our construction, and point B is the center of the circle also according to our construction. And because of the fact that BA equals to BP equals to BQ, we found out that BA equals to PB equals to BQ, and BA is the radius of the circle, and therefore BP and BQ must be also the radius of the circle that equals to R. So BA equals to BP equals to BQ equals to R. All those three line segments are the radius of the circle that equals to R. And for that reason, the circle must pass from points A, P, and Q. Why? Because this is exactly the division of a radius. The radius of any circle starts from the center of the circle and ends at the point of the circle itself. For that reason, those three radii, BA, PB, and BQ, they are all located on the circle itself. Or in other words, points A, P, and Q must pass for the circle itself. Or the circle itself must pass for these 3 points A, P, and Q, because all those 3 points A, P, and Q are the edge of the radii BQ, BA, and BP. So all those 3 points A, P, and Q are all located on the circle itself. And it is given us the question that DA is perpendicular to AB. So DA is perpendicular to AB, but according to our definition, AB is the radius of the circle. So DA is perpendicular to the radius of AB, and therefore DA is the tangent to this circle at point A. Repeat again. According to what is given us in the question, DA is perpendicular to AB. This is the sign of perpendicular. DA is perpendicular to AB. But according to our definition, AB is the radius of the circle, this is equals to R. So in total, we found out that DA is perpendicular to the radius R, and because of the fact that DA is perpendicular to the radius R, DA is defined as a tangent to the circle at point A. DA is tangent to this circle at point A. From this common point D, we have tangent DA that is tangent to this circle at point A. Likewise, from the same common point D, we have secant DQ that cuts this circle to points P and Q. So all the requirements of tangent secant theorem are satisfied, and therefore we can implement this point D, tangent secant theorem. So repeat quickly on tangent secant theorem. According to tangent secant theorem, if the tangent and the secant are drawn to a circle from the same external point P, here we have, this is the common external point P. From the common external point P, we have tangent PA that is tangent to this circle at point A. Likewise, from the same common external point P, we have secant PC that cuts the circle, those 2 points B and C. So in this domain, according to tangent secant theorem, the following equation is true. The square of the tangent's length, that is to say PA square, equals to the product of the secant's whole length and its external part. The length of this secant in total is PC, so it is PC times the length of the external part of secant PC, that is PP. So in total, PA square equals to PB times PC, or PA square equals to PC times PB, according to tangent secant theorem. So as I mentioned before, we can definitely implement tangent secant theorem on our domain if we focus on this common external point D. From this common external point D, we have tangent DA that is tangent to the circle at point A. From the same common external point D, we have secant DQ that cuts the circle at those 2 points P and Q. In total, the length of this secant is DQ, the external part of this secant dq is dp. So according to tangent secant theorem, dA squared, that is the length of the tangent squared, equals to dp times dq. So it is the product of the external part of secant dq times the length of this secant in total, that is dq. So dp times dq equals to dA squared. Once again, we shall find out that according to tangent secant theorem, if we focus on the common external point D, the following equation is to dA squared, that is the length of the tangent squared, equals to dp times dq. dp is the external part of secant dq, and this secant in total equals to dq. So it is the external part, the product of the external part, that is dp times dq. That is the length of this secant in total. So again, according to tangent secant theorem, the following equation is to dA squared, that is the length of the tangent squared, equals to the product of the external part of the secant, that is dp, times the length of the secant in total, that is dq. So dA squared equals to dp times dq. dA equals to x, and therefore dA squared equals to x squared, and it equals to dp equals to 1 times dq. dq in total equals to 1 plus 4 plus 4, that is 9. So in total, we actually found out that x squared equals to 9 times 1, or 1 times 9, that is 9. So x squared equals to 9. Here we took out the equation, and I found out that x equals to the square root of 9, that is 3. So I actually found out in total that the length of this line segment AD is equals to x is equals to 3 units. EP equals to x equals to 3 units. So on both methods, we actually found out that the length of line segment AD equals to x is equals to 3 units. Okay, thank you very much.